All right. So what we're going to do in this video here is we're going to look at actual data taken from PubMed about the avian flu, the novel H5 avian influenza, and this is considered a highly pathogenic avian influenza, and we're going to use it as a reason to learn about exponential decay. Now, there's a proviso that must be very clear at the beginning of this, which is this particular exponential decay model will not include any provision for the replacement rate of the condor population by reproduction. So it's going to either over or underestimate the total amount of death, or it's going to over or underestimate the total number of years. If we think of the replacement rate as being greater than either a replacement rate of greater than 2, so you have two parents, if they have more than 2 children, then the population increases over time. If you have 2 parents and they have less than 2 children, fewer than 2 children, then the population will decrease over time. If they have exactly 2 children and every condor pair always has 2 children, then the replacement rate would be completely static. We're just not going to consider it at all because we're going to focus on the mathematics. So, with that in mind, what does the data show? Well, as part of our empirical research, we visited several government agency websites that have been monitoring the death of both poultry-type animals and wild birds, of which the condor population falls into. They're not considered poultry. We don't eat them like chickens. And they belong to, remember, kingdom, phylum, class, order, family, genus, species. They belong to 2 separate orders. Falconiforms, so falcons like the peregrine, and then they have their own order, and I'm going to do my best here. Cathartiforms, okay? So there are some problems with this right off the bat of our study, of our analysis here, and I'm going to show you what those are. And this is actually a good time to explain something that students often find hard. That the more you can criticize your own study and its limitations, the more believable your results. I mean, you want to be honest, okay? So we're going to start by talking about the limitations of this analysis. Okay, limitations, deficiencies, okay? Let's say sources of error, like that. So this is kind of a lab notebook type entry, and what are the error sources? Well, we have a mixture of dates. What do I mean by that? So the total population, data comes from 2016. Okay, so we're talking about dead birds in 2023. All right, well, that means there's a gap in the data from 2016 to 2023, okay, of 7 years. So we have a 7-year mismatch, you know, and that's okay, because if that's the best data there is, I mean, we can't here in Palestine, Texas, expect to go count them, right? So we have to rely on what's out there on the scientific data. Only shows that the last time there was a comprehensive physical count of each bird was in 2016. And because there are so few of them, it was possible to count each and every one of them. So I'm going to use a symbol here for the sole purpose of showing you what the symbol means. It's a backwards capital E, and what it means is there exists. Okay, there are, or there exists, and I think we could say existed. Okay, that's what's in that E. So now that I've shown that, I'll just write it out. There are, and then I'm going to say approximately 446 condors. Okay, we should be clear here. When we say condors, we're referring to. So when I use the word condor in this sense, I'm only referring to the California condor, not the Korean condor or any other condor. Okay? Okay, so there's 446 condors, and during the study about the effect of this particular new evolution of the virus, there were two numbers that were given. They said there were 20 total dead birds over the 1 year that they studied. 20 total. That when they performed the forensic pathology of the birds, there was only 15 birds whose blood revealed the presence of, or ocular fluid revealed the presence of the H5N1 type virus, the avian flu. So which number should we use in our exponential decay calculation? Well, I think the reasonable answer is to use 15. Okay, so what does that mean? 15 dead over 1 year from the avian flu. Okay, I'm just going to say H5 to abbreviate that. Okay, so now what? We have two numbers. We have a total, right? And we have dead birds. So how many birds are left? Well, presume that you don't have a calculator and do the subtraction. 446 minus 15. Okay, 6 minus 5 is 1, 4 minus 1 is 3, and 431. So there are 431 birds that remain. Okay? Now, the next step is to perform a percent change. So maybe I should number this. This is just data, so all this right here was just given. Okay, so now we're going to get into the calculations. So step 1 is to calculate the percent change. Now I'm going to write the percent symbol and then draw a triangle. Once again, I'm trying to do two things at once here. I'm trying to teach you that this backwards E means there exists, and that this triangle means delta. That's the Greek letter, delta, and that delta means change. Okay? If I say delta V, I'm talking about change of velocity. Okay? So calculate percent change. And then I'm going to write Y-O-Y. What does that mean? Y-O-Y is year over year. Okay? Year over year. And that just means over the course of 1 year, what was the percent change in the total population of condors? Alright? So what's the setup? The setup is for you to recall that percent change works like this. New minus old, okay, over old times 100. And so since the new in this case is a smaller number than the old, this still applies just fine, but we're going to actually subtract. We have all the numbers we need. Okay, so new minus old. 431 minus 446 is going to be negative 15. I hope that's obvious from up here. Okay, so we'll go here and say 431 minus 446 over 446 is times 100. Okay, is equal to, here comes your negative symbol, negative 15 divided by 446 times 100. All right, so let's perform that division. And there's some fancy way to do it in here. I'm just going to do it on my calculator. If you want to do it on yours, that's good. So on my RPN calculator, I'm going to type 15, enter, put it on the stack, and then type 446, and then hit divide. And I'm going to get 0.0336. So this is equal to 0.0336. The next number is a 3, so it's not going to change it. Times 100. Okay, so the way that works is it just moves the decimal place over 2 places. And so what does that mean? That means that, remember, don't forget your negative symbol now. That's a negative symbol. So that means that there was a decline. Okay, negative means decline in the population of 3.36% from 2022 to 2023. All right. So the question is, I think it's important to write the question out if we're going to do this right. What is the research question here? What do you want to know? How long until, we'll just say we'll use a big P for population and the lowercase for T, and then C for condors. The total population of condors equals 0. Okay? How long? Well, here's how you start answering that. This is the basic form of an exponential, and I prefer to use the model I learned in business school rather than the one I see in the math textbooks, because it makes a lot more sense. You have your future value, okay? So we could think of this like the future population, okay? We're going to set that equal to 0. And then we have the starting value, or the present value. That would be like the current total number. And then we're going to multiply that by 1 plus the rate of growth or decay as a decimal. So in this case, it would be negative 0.0336. You're going to add that to 1, and then you're going to raise it to the number we're looking for, which is x. You really want to know what that is. Alright. So let's set the problem up, and then we're going to have to learn the rules for how we solve it. So the future value is going to be 0. and the present value, we'll set it at 446, and then we take that, get 1 plus, and then there was a negative 0.0336 raised to the unknown. So what is 1 minus 0.0336? Well, I would put 1 on the stack and then type 0.0336 and hit subtract. And what that gives me is, let's write this, that gives me 0.9664, okay, raised to x. Now what? Okay, well now you can't proceed without some idea of logarithms and their rules. So what we're going to do is quickly run through those rules, just so you can do it. So these are the rules. We're going to be using the natural logarithm here, but the rules for the natural logarithm. Okay? You don't really have to know what this is. You can just use the rules. Here's rule number 1. It's best shown by example. Okay? So if I take the natural log of x times y, what that does is it distributes, and it's the natural log of x plus the natural log of y. And it's that plus symbol that'll get you every time. Okay. So this was times, and now it's plus. Alright? What's the next rule? The next rule, number 2, is the division rule. So if I have the natural log of x over y, that's going to equal the natural log of x minus the natural log of y. I think they wanted us to discuss this. If I have the the natural log of 1 over y, I want you to think about something for a minute. Think about what 1 over y is the same thing as y raised to the power of negative 1. So this is also the natural log of y, and up here we got negative 1. Okay, here's the final rule, number 4. And that rule states that if you have whatever, y equals a, b to the x, if you take the natural log of the left side and the natural log of, remember this split up here, ln of a, and then you have plus ln of b raised to x. So now what? Well, now you can move the natural log of a out of the way over here, okay? But this is just an example. You'll see what we get to here in a sec. So now let's do it for real. Let's just write down what we have. So this is real world. Real work. How about that? Yeah. So we begin with we'll do let. Okay. Let future value be assigned the value of 0. Additionally, let the present value be assigned the value of 446. And now r, lowercase r, is equal to 0.0.
So anyway, they had a huge stack up there. City hall. I don't know the city council, the city manager. You got time? Come with me. I have to come here. There's this brand new sitting on the ground.
Checking my own work. Okay. Remember, this was negative. So going back to that formula, this one, the future value is going to be 0, present value is going to be 446, and except of doing 1 plus the rate, you're going to do 1 minus the rate. Okay. So 0 equals with 446 here. And inside, we're going to put the b raised to the x power. Okay, so now it's if I take the natural log of 0 and I take the natural log of 446 times b to the x, okay. Okay. So where we're at is here, okay? And if we go down here and look at our rules, we kind of have rule number 1 going on, and then okay, and then okay, I've done that. Good. All right. So, and then once we do rule number 1, we split it up like that. We'll move the terms around. I don't know what I wrote here. I need to put the data in here. This is the data right here. So what we need to do is we need to take the natural logarithm of 0 and then set that equal to the natural logarithm of 446 times, and then 0.9664 raised to the x. And when we do that, you'll get the natural log of 446 kind of by itself. And the natural log of 0 is 0. Okay, so you're going to write down ln of 446. And then remember that plus symbol goes there from rule number 1. And that's going to be the natural log of 0.9664 raised to the power of x. Okay, now we move this over here. Okay, this guy's going to come over here. It'll have a negative sign in front of him. And we're going to write negative natural log 446 is equal to, and then now we can apply the fourth rule, where we bring, I never showed the fourth rule. If you take the natural log of A, B, well, I should just say, hang on. If you take the A times the natural log of B raised to the power of x, that's equivalent to A times x natural log times natural log of b. I'll show you what's happening. So, because this is one of those things where if I fly past it, you won't get it. If I just slow down for just a minute, you'll get it. What's happening is this guy is coming down here. All right, that's all that's happening. Like, so now I have a times x times the natural log of whatever this says. Okay, b. Okay, that's all that's happening. So back to our actual problem. See, there's the x, right? It's going to come down right here. And then you'll have ln of 0.9664. So we already moved this guy over the ln of 446. And so I just want to now finish this up and say, what I'm going to do is pull this x down right here, okay? So I'm going to say x times the natural log of 0.9664. Well, now, how do you isolate the x? You just divide, right? To get rid of, if it's times, you get rid of it by dividing. dividing. So we're going to divide both sides by the natural log of 0.9664. Natural log of 0.9664. Okay. So, if you look at the left side, it's kind of where the work is, because x is now solved for on the right, and it's going to be this divided by that. So it doesn't, the negative sign doesn't make any difference. So we'll just put 446 and hit natural log. I get 6.10. This is going to be approximation here. 6.10 divided by 0.9661 or 4. Okay, I got negative 0.0342. Negative 3, 4, 2. And now that I see we're going to have some signs, that negative sign up top becomes important. Okay, then negatives cancel out. What we'll do is just hit divide the top by the bottom, and what you get is approximately 178 what? What did this represent? What did X represent? Okay, X represented time in years. Okay, according to this model, let's write it out. According to data from the National Institute for Health, if avian flu, we'll just say California Condor death rate continues at 3.36%. For 178 years, the population of California Condors will equal 0. Okay? So, I thought what would be good now is to model this by looking at Desmos. Okay? Okay, this is Desmos, as you recall. Come back here, and right here is where our problem is, right here. Okay? And then over here I just had a 0. I'm going to put an f of x there. I'm going to say f of x equals. Okay, so if I want to model this, I'll show you what to do. Now, it equals 446, okay, times 0.9664 raised to the x equals 446 times 0.9664 raised to the x. Okay? Now it doesn't know what to do, and so what we're going to do here is we're going to say f of x sub 1, and then instead of saying equals, we're going to put this, instead of saying equals, we're going to put this symbol here and say a, open parentheses, b, close parentheses, and then up here x sub 1. Okay? And now it's giving us the statistical data here. Okay, so now let's see if it plotted. And let's zoom out. Yep. So look at that. It's a nice exponential decay function there. Remember, this assumes that there's no growth, and so what appears to be happening, like if you wanted to interpret this graph, is, would you say the slope is steeper here, and then when it gets to about year 50, we start to see it even out. Yeah, and then so there are fewer and fewer, so they're dying at a slower rate and an absolute number. And so that's an exponential decay curve. So we didn't do it wrong. And the y-intercept should be 446. Bingo. Okay? That's the y-intercept. So that, yeah, there you go. That's what it looks like. Now, should it look like this? No, no. We could model this differently and flip it so that we're showing like deaths rising. Okay, you should see like an S curve, not like this, where you would see this shooting up into infinity like that. But I hope that helped a little bit. At least a little bit better than the original video. And nothing beats practice, right? So you'll get. I was real confused by anything that started with logarithms. I didn't understand them at all, and I still don't get logs. And they say base 10, base, and they change the base, and I just get confused. That's why I like natural logs, because it seems like they work easier. Okay, we're going to end the video there, and make sure to like and subscribe. If you haven't already, I want you to go to the store and get a very big hammer and just absolutely obliterate obliterate that like button. Okay, and hit that notification bell so you're always updated when I release new videos on this channel. All right, thank you and bye for now.